Welcome students, welcome to the last video of design of PSC end block. So in the last video we learned the investigation of Anchorage zone stresses using Magnus method and Guyon's method. So in this video we'll learn the investigation of Anchorage zone stresses using Zielinski and Rowers method and IS-Code method. In Zielinski and Rowers method, the end of the PSC post-tension beam is considered as a surrounding prism of size 2y0 by y0. So this is 2y0 by 2y0. The size of this prism is considered. Under this prism, a loaded area or the punching area of size 2y0 by 2yp0 by 2yp0. So which is the depth of the anchor plate. So this loaded punching area or the loaded area is considered into the surrounding prism. And this is the distribution diagram. The zero stress point of zero stress is 0.3 y0, and the point of maximum stress is 0.5 y0, and the total stress distribution is still 2 y0 from the face of the anchor plate. So this is the maximum tensile stress at a distance of 0.5 y0 from the face of the anchor plate. So this is the tensile stress distribution for the design of end block using Zielinski and Rowers method. Now this 2y0 is nothing but the surrounding side of the surrounding prism. 2yp0 is the side of loaded or the punching area. Yp0 by y0 it is again the distribution ratio as we considered in the Guyon's method. Fe is the transfer stress as usual. Fc is the average compressive stress, which is taken as P by A. This Fv the transfer stress. Fv is the transfer stress. This Fv is transfer stress is calculated using this expression Fv max. Fv max is equal this. Fv max is the maximum tensile stress. This Fv max is determined using this expression. Fv max is equal to Fc Fc point into 0.98 minus 0.85 into 0.825 into Yp0 by y0, that is the distribution ratio. This Fv is the transfer stress. Pk is nothing but the applied compressive force on the end block. We took it P in case of Guyon's method and Magnus method. Now here it is Pk, which is the compressive force on the end block. Fbst is the bursting tension force. We took it PBST in the Guyon's method. So this FBST is calculated using this equation. FBST is equal to Pk into the 0.48 minus 0.4 Yp0 by y0. This Fv max is valid with a ratio of between Yp0 by y0 equal to 0.3 to 0.7. If suppose we already know that the concrete also will take some tension. Suppose that is also if we allow to consider that the concrete is taking some tension, then we can calculate the corrected bursting force. So that bursting force can be considered as FBST corrected is FBST without considering, which we have calculated without considering the tensile strength of concrete, into 1 minus Ft by Fv max square, where Ft is the permissible tensile strength of concrete. In Guyon's and Magnus method, we didn't consider the tension taken by concrete. We didn't allowed for the tension taken by the concrete. So, but Zielinski and the IS-Code method allows to consider the tension which is taken up by concrete. There is an important note here in Zielinski. If 2y0 exceeds the width of the section B, 2y0 is nothing but the size of the surrounding prism, so which is usually taken as the width of the section B. Suppose if that 2y0 is exceeding the width of the section B, then the surrounding prism is restricted to size B by B. That means it cannot exceed 2y0. 2y0 should not exceed value of B in case of Zielinski and Rowers method. Now let us solve a problem on Zielinski and Rowers method. The same problem of first problem we solved it by Baglan's and Guyon's method. The same problem is here now. Let us solve this problem using Zielinski and Rowers method. First we'll draw the section. The size is 120 by 300 and this is concentric plate, anchor plate of depth 75. Mm. Now this is nothing but the distance of from the base to the center of the anchor plate is nothing but your y naught. So therefore y naught is 150 mm as similar to the Guyon's method. So 2 y naught is equal to 300 mm. Now this 300 mm is, now we have to check this 2 y naught value with respect to the width of the section. So this is greater than the value of b, which is 120 mm. So that means 2 y naught value need not to be more than b. So therefore the prism is, the square prism is restricted to size b by b, that is 120 mm by 120 mm. So therefore 2 y naught value should be limited to 120 mm. And 2 yp naught is the depth of the anchor plate, which is 75 mm. It is 75 mm. P value is given as 250 kilonewton. So this is the size. This is the punching area and this is the surrounding prism. So this is 2 yp naught by 2 yp naught and this is 2 y naught by 2 y naught. The size of the prism is 2 y naught by 2 y naught and the size of the punching area is 2 yp naught by 2 yp naught. Now calculate FV max first. So FV max, before calculating FV max we require FC for that. So FC is average compressive stress in prism. So this average compressive stress is P divided by the area 2 y naught by 2 y naught. So 250 into 10 to the power of 3 divided by 120 by 120. So FC is 17.36 Newton per mm square. Now this, knowing FC value, you can calculate the FV max, maximum tensile stress. So it is FC into, as per Zielinski, FC into 0.98 minus 0.825 into the distribution factor yp naught by y naught. So this FC value is 17.36, 0.98 minus 0.825 into the distribution ratio 75 to y naught is 2 IP naught is 75 by 2 and 2 Y naught is 120 by 2. So this FV max is YP naught is 75 by 2 and Y naught is 120 by 2. So that 2 get cancels. Now FV max is 8.06 Newton per mm square. So this is the value of FV max. Now calculate the bursting tension force. Before that, what we can do is we can draw the distribution. This is the distribution. The maximum value is 8.06 Newton per mm square. And the point of zero stress is 0.2 Y naught. Point of maximum stress is 0.5 Y naught. And lastly 2 Y naught. So you can write these values 0.2 Y naught, the distance values you can measure. You can calculate and write these distances. Alright, now the bursting tension force, this is FV max and this is the distance along x direction. 0.2 y naught you know, y naught is 2 y naught is 120, so y naught is 120 by 2, that is 60 into 0.2, that distance, and 0.5 y naught is 0.5 y naught similarly, and 2 y naught 2.2 y naught is 120, so total is 120. So like this you can draw the distribution. Now the bursting tension forces, the area of this diagram, you can calculate the area of this diagram, or the formula given by the Zielinski is FBST is equal to PK into bracket 0.48 minus 0.4 YP naught by Y naught. So PK value is 250. So let it be in kilonewton, you'll get it in kilonewton. So 0.48 minus 0.4. YP naught is 75 by 2. And this is Y naught is 120 by 2. 2 get cancels. So this is FBST in kilonewton, you'll get it as 57.5 kilonewton. Now this ends the problem. Now if suppose further in the same problem, if it is asked to consider the allowance for tensile strength of concrete, then suppose if allowance is made for tensile strength of concrete, that means you are considering the tensile strength of concrete, so your FBST will be reduced. Say you require FCK, now FCK is not there in this problem, let that FCK be 40 Newton per mm square, suppose it is M40 grade concrete, then your tensile strength of concrete will be, determine the tensile strength of concrete. FT is equal to 0.24 root of FCK. So FT is 0.24 into root of 40. So you will get it as FT equal to 1.5 Newton per mm square. Now calculate the bursting tension force corrected. So FBST corrected is equal to formula FBST into bracket 1 minus FT by FV max square. So FBST you have calculated as 57.5. 1 minus FT value is 1.5 divided by FV max is 8.06 square of this. So your corrected value will be 55.5 kilonewton. So you can see the values. The earlier value was 57.5. Now when you have considered the tensile strength of concrete, then the FBST is 55.5, which has reduced now. So this is the end of the problem, first problem, which is concentric. Now we'll solve another problem of eccentric problem, which we have solved under Magnus and Guyon's method. This is the problem, the same problem which we have solved. Let us solve this problem by this. First of all, we'll draw the section. This is the center of the section. This is the upper curve. This is the bottom curve, and the anchor plate is coinciding the bottom curve. So this is the anchor plate. This is 66.6, 66.6. Right. Now your y naught is the center of this anchor plate from the bottom. So this is y naught value. Now the y naught value is 66.67. So therefore 2 y naught will be 133.33. Now this is greater than again the width of the section. The width of the section is 100 mm. So this is again greater than 100 mm. Therefore you have to restrict 2 y naught to, therefore 2 y naught you have to restrict it to 100 mm. So surrounding prism is 100 by 100. So 2 y naught is 100 mm. So 2 yp naught is the depth of the anchor plate, which is 50 mm. P value is given as 100 kilonewton. Now calculate FC, average compressive stress in prism, which is P by the area 2 y naught by 2 y naught, prism area, which is equal to 100 into 10 to the power of 3 divided by 2 y naught, 100 by 100. So your FC comes around to be 10 Newton per mm square. So this is value of FC. With FC you can calculate FV max. So your FV max equation is FC into bracket 0.98, 0.825 into yp naught by y naught. So FC value 10.98 minus 0.825 into 50 by 100. So this FV max comes around to be 5.675 Newton per mm square. When you know FV max now, you can draw the distribution. This is the distribution. Point of zero stress 0.2 y naught, point of maximum stress 0.5 y naught, and end is 0.2 y naught, 2 y naught. So maximum is 5.675. You can calculate these distances and show. Right? And your FBST will be formula pk into bracket 0.48 minus 0.4 into yp naught by y naught. If you substitute and calculate, you will get 28 kilonewton. Still, if you require the corrected value by allowing the tensile stress considered tensile strength of the concrete, then your FBST corrected will be will be 26 kilonewton. Right, you can take M40 grade concrete. So this is how you can design the end block using Zielinski and Rowers method. You can calculate the stress. With this stress, you can calculate the area of steel. If you want area of steel, AST equal to FBST divided by the formula 0.8 Fy. So this is the end of the problem in by Zielinski method. Now let us consider the IS-Code method. So this IS-Code method is similar to that of your Zielinski only. So only thing is the formula remains different. It is the continuity of Zielinski. Whichever we have solved the problem by Zielinski, the same you can solve. Only thing is FV max, FBST formula will change, nothing else. So this IS-Code method is the method based on the works of Zielinski and Rowers method. The bursting tension force is FBST is equal to PK into bracket 0.32 minus 0.3 YP naught by Y naught, as against it was 0.98 minus 0.825. Only these fractions are changing. Sorry, 0.4 it was 0.48 and 0.48 minus 0.4 it was. Now here 0.32 minus 0.3 it is, where Pk is the tendon janking force. Yp again, Yp naught by Y naught is the distribution ratio. The maximum tensile stress is Fc into 0.98 minus 0.825 Yp naught by Y naught. That is, this equation remains same as that of the Zielinski. Only thing is FBST is changing here. The average compressive stress Fc is again P by 2 Y naught by 2 Y naught. The reinforcement, the designed reinforcement is distributed in the zone of 0.1 Y naught to 2 Y naught. But in Zielinski, it was distributed between 0.2 Y naught to 2 Y naught it was. Now here it is 0.1 Y naught to 2 Y naught. That means 0.1 Y naught to 0.1 Y naught is the point of zero stress starting, and 2 Y naught is the end. So this is how you can solve the problems using IS-Code method. Let us solve two problems on IS-Code method. We are not considering the same problems now. You can solve already Zielinski and Rowers method problems have been solved. Only thing is FBST equation is different. You can solve the same problem similarly. Now let us take Anchorage zone reinforcement. Let us design using IS-Code method. So the first problem. There is an Anchorage 125 mm diameter carrying 12 wires of 7 mm dia. This is the data given. Now we have to solve this problem using IS-Code method. Right. This is a problem now. Let us solve. This is I section now. The diameter, 12 wires of 7 mm diameter are stressed to 950 Newton per mm square. It is embedded concentrically in the web. So 12 wires are concentrically embedded into the web of I section. The thickness of web is mentioned here. So let us draw this section. This is the I section. Right. The size is not mentioned. So the diameter is mentioned as 125 mm is the diameter. 125 mm is the diameter of the anchorage. So this is the anchor plate, which is circular now. Instead of rectangular, it is circular now. And this diameter is 125. This is the surrounding prism now, which is 225 mm. Right. Now to solve this, first of all, we have to convert the area of the cone into the equivalent or loaded area. So because as it is a circular anchor plate, so you have to convert this. So therefore area of cone is equal to the area of equivalent loaded area. We know that area of cone pi by 4 into d square is equal to the loaded area is 2 yp naught by 2 yp naught, right? So therefore 2 yp naught is substitute, we know the diameter is mentioned here. 2 yp naught is value you will get 2 yp naught value, so that 2 yp naught value is 111 mm, right? So this is the punching area 2 yp naught, because as it is not a rectangular, it is circular. So if it is a rectangular, then you would have taken the depth of the anchor plate, but now as it is a circular, you have to convert it to equivalent area and find it. So this is how you can calculate 2 yp naught as 111 mm. Now the prism size, the prism is restricted to area 225 by 225. Now instead of taking B by B, now this is I section, so you have to restrict it to BW by BW, that is width of the web, BW by BW. So width of the web is 225 mm. So therefore your 2 y naught value will be equal to 225 mm. Because the size is not mentioned, size of the section is not mentioned, so directly you restrict 2 y naught to 225 mm. Pre-stressing force is not mentioned, instead the stress is mentioned. The stress is 950 Newton per mm square. So pre-stressing force, calculate pre-stressing force. Pre-stressing force is equal to the stress into the area. Stress is 950 and the area of the steel is pi by 4 into the diameter is 7 mm diameter of how many bars? 12 wires of 7 mm diameter. So pi by 4 into 7 square into 12 numbers. So you'll get it P value as 438.7 kilonewton. We'll get it in newtons, so convert that to kilonewton. So this is the value of P. Now the your FBST is Pk into bracket. Equation as per IS-Code is 0.32 minus 0.3 yp naught by y naught. So substituting the values, 0.32 minus 0.3 into yp naught 111, y naught 225. So your FBST value will be in kilonewtons 75 kilonewton. So this is the bursting tension force FBST. Now with this FBST you can calculate the area of steel. Area of steel AST is equal to FBST divided by 0.87 Fy. So FBST is 75 into 10 to the power of 3 in newtons, 0.87. Now Fy is not mentioned, Suppose if the Fi value will be given to you. If not, now I am assuming it as 250. You can take HYSD also, HYSD 415. Calculate the area of steel. So if I take it 250, it is 345 mm square. This is the area of steel. Considering Fy equal to 250 Newton per mm square. Right, your design strength will be 0.87 Fy. Design strength is 0.87 Fy, and therefore your AST will be FBST by 0.87 Fy. And now this is the area of steel required, which is 345 mm square. You can convert to number of bars if you want, and if it is asked to draw the distribution, you can draw the distribution also. So we'll solve the distribution detailing in the another problem immediately after this. So this is the problem, right? Similarly, in the previous problem also, if the anchor plate is not rectangular, if it is circular, let it be in any of the case like Zielinski method or Gion's method, then you have to calculate the area 2yp naught in the similar way by considering this. So let us solve another problem of detailing, last problem. So this is the last problem on detailing. Thus the end block of a post tension beam, it is 300 mm by 300 mm subjected to concentric anchorage force value is given by a Fresnel anchorage system. The area is mentioned. The design and detail the anchorage zone reinforcement for the end block. Now you have to continue till the detailing. Now let us solve this problem. Now this is 300 by 300. So it is a square. (300 by 300). And you have a circular anchorage system here, which is concentric. The circular anchor plate. Now you have to determine the equivalent area. This will be the equivalent area. So that you can consider this as 2y naught. This is 2yp naught by 2yp naught. Right. Now calculate the p value is mentioned. P value is 832800 newtons. And the area of this anchor plate is mentioned as 11720. Anchorage system area. This is the anchorage system area 11720. So calculate the equivalent. It is again circular, so you have to calculate the equivalent area. So 2yp naught by 2yp naught value is the punching area is the area of the anchor plate, which is 11720 mm square. Right. So therefore 2yp naught will be equals to 108 mm. This is the 2yp naught value, and this is 2y naught value. So 2y naught is 300 mm. So when you know 2yp naught and 2y naught, calculate FBST. Pk into bracket 0.32 minus 0.3. The same problem you can solve it in Zielinski method also. Only thing is equation differs, FBST equation differs. So this is this, if you substitute, you'll get it 176.5 kilonewton is the FBST. You can calculate maximum stress also. For that you require FC is equal to P by A direct stress. P is area of pre-stressing force, 832,800 divided by area, the surrounding prism area, 2y0 by 2y0, 300 by 300. P by 2y0 by 2y0. So you'll get it FC as 9.3 Newton per mm square. Maximum tensile stresses, FV max is equal to FV max FC into 0.3 FC into 0.98. If you want the formula, I can give you the formula again. FC into bracket 0.98 minus 0.825 into 2IP0 by 2Y0. 2IP0 by Y0 or 2IP0 by 2Y0. So this is 9.3 into 0.98 minus 0.825 into the ratio 2IP0 by 2Y0 ratio will be 0.36, the distribution ratio. You can calculate earlier and substitute here now. So your FV max will be 6.35 Newton per mm square. Now you know the FBST value. With that FBST value, you can calculate the area of steel. So that area of steel is AST formula, area of steel. Area of steel required, AST is equal to FBST divided by 0.87 Fy. Now this problem Fy is not mentioned again. So for this problem I will take it as 250 again, a mild steel. Now which is now absolute. You can take HYST if you want. If it is not mentioned, take minimum value as 415. So FBST is 176.5 into 10 to the power of 3, that divided by the design strength 0.87 Fy. Fy is 250. Let Fy equal to 250 Newton per mm square. So you'll get the area as 810.75 mm square millimeter. This is the AST required. Now with this AST required, you have to calculate the number of bars. Now let us assume 10 mm diameter bars. Assume 10 mm dia steel links with yield stress of 250. While practicing, you can take it 415 and you can practice. So if you calculate the number of bars here, number of bars required is equal to AST divided by A5. AST is 810.75. Diameter of single bar is pi by 4 into 10 square. So you'll get approximately 11 bars. But if you want, now we have to provide these steel in a form of a mesh. So therefore you require even numbers. So let it be 12 bars. Let equal to 12 bars. Now this 12 number of bars you have to distribute between the distance point 1 y0 to y0. Now there we have distributed between, in Zielinski it was 0.2 y0 to y0. Now this reinforcement is to be arranged in the zone between 0.1 y0 to y0. So 0.1 y0 is 15 mm and y0 is 150 mm. So between 15 mm to 150 mm you have to distribute the bars. Now you are providing 12 bars in each direction in a form of a mesh you have to provide. So provide 12 bars in each direction in the form of mat or mesh, right? So there will be, so you require total 12 bars now in x direction as well as in y direction. So you should think whether you have to provide 3 meshes or 4 meshes of how many bars. So you can provide 4 meshes, you can provide 4 bars along each direction in 3 meshes. So it will be 12 bars, right, in both the direction. You have to provide 4 number of bars in both the direction x and y direction, so that you will get one mesh. So like this you have to provide 3 meshes so that you will get total 12 bars in x as well as in the y direction. So the detailing is, this is the detailing. See, 2 y0 is 300 mm. This is also, this is 150 mm. That is, you have to distribute from 0.1 y0 to y0. That means you have to distribute from 15 mm to 150 mm. Clear? So you have to provide how many bars? 4 bars. 1, 2, 3, 4 and 1, 2, 3. So 12 bars. So total 12. So 12 of 10 mm diameter bars in y and z directions. So this is the mesh. You get it for size of 300 mm by 300 mm. So this is the distribution. From the face of the anchor plate, it is how much? 0.1 y0. So 0.1 y0 is 15 mm, right? And you have to distribute between 0.1 y0 to y0. So that means till 150 mm you have to distribute. So from 150 mm subtract this 15 mm. So whatever is the remaining, you have to divide into 2. So it will be 67.5 and 67.5 mm remaining. So this is how you can provide the steel into number of meshes, right? So this ends the problem. This is a detail. 2 yp0 is the depth of the anchor plate, 108 mm. So this ends the problem on IS-Code method as well as the Zielinski and Rowers method. So this ends the module 5 complete. Thank you.